Hello, my name is Professor Yanofsky, Noson Yanofsky. We're doing, this class is called Discrete Structures. We're doing section 4.4 of the book, Ross and Wright book. The topic is called Recursive Definitions. Okay, so we have to remember, this is very much related to mathematical induction. Same type of thing, but here we're defining sequences. So let's remember what a sequence is. Okay, remember a function f from the natural numbers to the real numbers is a sequence of real numbers. It tells you what the zeroth number is, what the first number is, what the second number is. We had this before. Okay, so it's a sequence. Okay, let's remember. We did that already, but now let's go like this. Definition. A sequence F is defined recursively. Defined recursively if it is given some base value. Okay, the word base, we saw that as in base case, okay? And f of n plus 1 is defined, determined by a formula of earlier values. You'll see in a second, you'll see examples that'll make that sense. So how do you figure out f of n plus 1? Look at earlier values. F of n minus 1, a couple of things like that. Okay, so let's do extremely easy examples. Okay, factorial of 0, that's the first, so we're defining a sequence. Factorial is a function. The factorial of 0 is equal to 1. Factorial of, of n plus 1 is equal to n plus 1 times factorial of n. Okay, sorry, let's make that a capital letter. Okay, we just did this last section when we talked about recursive functions. Let me just write it another way. 0 factorial is equal to 1, and n plus 1 factorial is equal to n plus 1 times n factorial. We saw that last time. Okay, so let's say we wanted to calculate what 5 factorial is. Well, you say 5 factorial is 5 times 4 factorial. 5 times 4 factorial. Okay, great. What's 4 factorial? Answer, 5 times 4 times 3 factorial. What's 3 factorial? This is equal to 5 times 4 times 3 times 2 factorial. What's 2 factorial? This is equal to 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1. Okay, finally you're going to get to 0 factorial. 0 factorial is 1. Okay, so that takes care of that. That's an easy example. Okay, here's another example. Here's another example. Now, okay, I'm assuming you've seen factorial. You probably programmed it. Why did you program it? You probably programmed it in the first semester programming because it's a nice example of recursion. Recursion, recursive definition. Same thing, same concept. Also, you'll see this has the same thing as mathematical induction. You give the base case, you give the induction. Okay, let's just do another one. This is another example. Fibonacci of 0 is equal to 1. Fibonacci of 1 is equal to 1. And then finally, Fibonacci of n plus 1 is equal to Fibonacci of n plus Fibonacci of n minus 1. This is what I was talking about. N plus 1 is determined by earlier values, not just an earlier value, which we had before, but earlier values. Just like that. Anyways, you want to figure out the 7th Fibonacci number. Well, it's very simple. It's Fibonacci of 6 plus Fibonacci of 5. Oh, what's Fibonacci of 6? Well, this is equal to Fibonacci of 5 plus Fibonacci of 4. Don't forget Fibonacci of 5 here. What's Fibonacci of 5? It's Fibonacci of 4 plus Fibonacci of 3. Okay. Okay, great. And you go on. I don't want to do this. I'll do it another way very quickly. Here's your Fibonacci numbers. This is the 0th place, the 1th place, the 2th place, the 3rd place, the 4th place, the 5th place, the 6th place, the 7th place. So you do it as follows. 1, 1, 1 plus 1. Now you fill in the rest of the things by looking at the earlier values. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So fib of, if you work this all out, you'd get 21. Okay, great. So that's another nice example. Let's do another example. Consider the following. Sum of n is equal to the sum of I equals 0 to n of 1 over I factorial. Okay, this is a regular definition. That's a standard definition. Add up all the numbers from 1 over I factorial. Okay, I'd like to give you the same definition, but a recursive definition. You will like recursive definitions because they're a little bit more clearer in some sense. Okay, this goes as follows. Sum, first I have to give you the base case. Okay, sum of 0, let's see, 0 to 0, 1 over 0 factorial. 0 factorial is 1. That's equal to 1. That's pretty easy. Okay, and finally, sum of n plus 1 is equal to sum of n. Okay, and you add up from all, you want to go till n plus 1? Very simple. Go till n, you did that, and then manually manually means with your hands, write in, okay, the last one. So what's the last one? N plus 1 factorial. Okay, and we can ask ourselves, what is sum of 3? Okay, so let's figure it out. Sum of 3 is equal to sum of 2 plus 1 over 3 plus 1 factorial. 3 plus 1 factorial is 4 factorial. 4 factorial is 4 times 3 is 12 times 2 is 24. 24. Okay. Hold on. What's sum of 2? So this is equal to sum of 1 factorial plus, okay, don't forget the 1 over 2 factorial. Somehow we got lost 3 over here. 3 times 2 is 6. No, that's stupid. 3, so this is 3. 3 times, oh, sorry. So plus 1, hold on. And we say, hold on. Okay, this is sum of 2 is sum of 1 plus 1 over 2 plus 1 is 3 factorial. 3 factorial is 6 plus, don't forget, 1 over 24. 1 over 24. Okay. Sum of 1 is equal to, so this whole thing is equal to sum of 1, which is equal to sum of 0 plus 1 over 1 plus 1 is 2 factorial. 2 factorial is 2 plus 1 over 6 plus 1 over 24. Sum of 0 is equal to 1. So this is equal to 1 over 1 plus 1 over, well, 1 over 1 is just 1 over 2 plus 1 over 6 plus 1 over 24. And that's exactly what it was. Okay? It's 0 factorial, that's that, plus 1 right, sum of 3. So sum of 3 is 0, 1, 2, 3. Right? Till finally we get to, right, so 0 factorial, 1 factorial, could have made a mistake there, plus 3 factorial, plus 4 factorial. Okay, I probably made a mistake here, but that's okay. Okay, let's do another problem. Okay, I won't make a mistake again. I'm off by a number somehow, but you can figure out how. Okay, let's do another one. Here's a recursive definition. S of 1 is equal to 0. S of n, instead of giving it by n, I'm going to give it n plus 1, I'm going to give it by n, is equal to S of, the floor of n over 2 plus 1. Okay? Let's plug in a few numbers and then we'll see what's going on. Let's say I did 15. So S of 15 is what? Well, what's 15? 15 divided by 2 is 7 point something. Okay, so 7 point some, so this is equal to 7 point something, but 7 point something floor is 7.5. 7.5 floor is 7. Okay, that's good. Plus 1. Okay, great. What's S of 7? S of 7 is equal to 7 divided by 2 is 3. 7 divided by 2 is 3.5. Floor is 3 plus 1 plus 1. Great. What's S of 3? So this becomes S of 3 is 3 divided by 2 is 1. Okay, plus 1 plus 1 plus 1. Great. What's S of 1? 0. So this is equal to 3. So S of 15 is 3. Okay, great. Let's just do S of 16. S of 16 is S of 8 plus 1, which is equal to S of 4 divided by 2 is 4 plus 1 plus 2, great, which is equal to S of 2 plus 1 plus 2 is 3, okay, and this is equal to S of 2, this is equal to S of 1 plus 1 plus 3, which is equal to 0 plus 4, which is equal to 4. Okay, so 15 is 3 and 16 is 4. What's going on? Every time I divide by 2, I'm adding 1. Now, what we're asking is the following question. How many times can I divide by 2? Well, we know this. We know this function. S of n is equal to the logarithm base 2 of n, the floor of that. See? I plug in 15, I'm going to get 3. Not 3 point something something. I plug in 16, I'm going to get 4. Okay? I plug in, again, let's just go through what happened here. How every time I divided by n by 2, every time I was able to divide n by 2, I added 1. So that's exactly what logarithms are all about. Okay, let's write up logarithms. Well, anyway, so that's the floor of the logarithm. It just gives you the whole number version of the logarithm. Let's build on this example, and let's look at another one. Okay, and it's as follows. T of 1 is equal to 1, and T of n is equal to 2 times T of n over 2 floor stop. Okay, so let's plug in some numbers here. What are we doing? Look what we're doing. We're multiplying by 2 every time that we can divide by 2. So it's interesting. Let's just work out some numbers. Okay, let's do T of 7. T of 7 is equal to 2 times 7 over 2 is 3, the floor of that, T of 3. Okay, okay, what's T of 3? By the way, we're right over here. What's T of 3? So this is equal to 2 times T of 3 is T of 1. 3 divided by 2. 3 divided by 2 is 1.5. Floor is that. T of 1 is 1. So that's equal to 2 times 1, which is equal to 4. Okay, so T of 7 is equal to 4. Okay, we'll figure out what that means in a second. Let's do T of 9. T of 9 is equal to 2 times T of 9 divided by 2 is 4. T of 4, 4.5. Floor is 4.5. Okay, T of 4 is equal to 2 times T of 2. Okay, and T of 2 is equal to 2 times T of 2 is equal to 2 times T of 1. T of 1 is 1. So we stop there. So that's equal to 8. Okay, 7 is 4. 9 is 8. Let's do a bigger number so we can get a feel for this. Don't need so much room. Don't need this anymore. Okay, and we do T of 75. Let's do T of 75. Okay, so let's work it out. This is equal to 2 times, so what's 75 divided by 2? 35 is 70, 36, 37. I think that's 2 T of 37. 37 plus 37 is 74.5. We're going to do the floor. So this is equal to 2 times, I think it's 18? 18. Okay. 18 is equal to 2 times, 18 divided by 2 is 9. Oops, I forgot a 2. T of 9. Okay, and so this is equal to 2 times 2 times T of 4. Okay, every time we can divide, we multiply by 2. Okay, and so this is equal to 2 times T of 2. And so this is equal to 2 times T of 1. T of 1 is 1, so we stop there. So this is equal to 1, 2, 3, 4, 5, 6, 64. T of 75 is 64. Let me show you what this function is. Okay, you can figure out what the function is. Notice what we do. Whenever we can divide by 2, we multiply by 2. That's the basic idea. And so we can write it, again, it has to do with logarithms also, but it's an interesting thing. It's equal to T of n is equal to 2 to the floor of log of n base 2. Okay? Now, that's an interesting function. If I left out the floor part, 2 to the log base 2 of n is n. Okay? So this is the integer, this is equal to the integer that is below the log. The next integer is below the log. So we did 75, 60, we got out 64, and that's very nice. Great. Okay. I'd like to do an example that could be done in last chapter. Now that we know what these sequences are, I want to show you a mathematical induction done with a sequence. So now that we know sequences and we know mathematical induction, we can do this. So I'm going to define, let's define, so this is a mathematical, this is a recursive definition, okay, and it's as follows. S0 is equal to A. Whatever A is, it's some number, doesn't matter. Sn, instead of doing it the n plus 1, we're going to do the Sn, is equal to 2 times Sn minus 1 plus B. Okay? So this is a recursive definition. We define the S terms. I'm not writing this as a function, I'm writing this as subscripts, but it doesn't make a difference. Okay? Sn as the 2 times n, okay? I'm writing the Sn term in terms of earlier values. So this is a recursive definition. Okay, great. Now I have a theorem. So this is a nice definition. Nothing to fight about. Now I have a theorem. Okay? By the way, if I wanted to figure out what S of 7 is, I would have to do, this is equal to 2 times S of 6 plus B. Okay, great. What's S of 6? So this is equal to 2 times S of 6 is equal to 2 times S of 5 plus B. Plus B. Okay? And then I'd want to figure out what S of 5 is. It's a big pain in the neck. So I have a secret formula. The theorem is a secret formula. It says as follows. Sn is equal to 2 to the n times A plus 2 to the n minus 1 times B. Okay? Notice this theorem does not, this gives you, this is a real live thing. S of n is going to give you a number. You give me, I mean, A and B are given in the beginning, but it's a real number. You don't have to do like I was doing here. This gives you the secret formula. Okay? It's a theorem. I'd like to prove it. Proof. Okay? The proof is by mathematical induction, and we became big fans of mathematical induction. So let's do it. The base case says, let's start the base case as 0. S of 0 is equal to, I want to hope that this is true, so this is going to be 2 to the 0 times A plus 2 to the 0 minus 1 times B. Is that true? Question, is that true? Okay, well, what's S of 0? S of 0 is equal to A. That's what, by definition, S of 0 is equal to A. Good, what's this equal to? 2 to the 0 is 1 times A is 1 times A. 2 to the 0 is 1, minus 1 is 0 times B, plus 0 times B, which is equal to A. It works out. Base case works out. A is equal to A. Again, what I'm doing is I have two different definitions of what a S of n is. One is a recursive definition, and one is a regular definition. And I'm trying to show that these two definitions are the same. Okay, great. So that's the base case. I didn't write base case. Okay, now the inductive case. Okay, let's do it. Assume, what are we assuming? We want to do this for the we want to do this for n is equal to k. So what do we want to show? We want to show s sub k for any k is equal to 2 to the k times a plus 2 to the k minus 1 times b. Excellent. Okay, good. That's what we assume. What do we want to do now? To show s to the k plus 1, okay, this is my cheat sheet, so I better plug in k plus 1 over here, equals 2 to the k plus 1 times a, times a, plus 2 to the k plus 1 minus 1 times b. Okay, that's what we want to show. That's our cheat sheet. Great, let's do it. Let's do it. So, s of k plus 1 is equal to, you know what I'm going to do? I want to write this out. I want to prove this definition. Okay? So I can't use this definition, but I can use the standard definition of what it is. This is the standard definition of what things are. This is a recursive definition, fine, but we have it, so let's use it. So this is equal to, by definition, so let's write that, by definition, this is equal to 2 times s to the k, well, k plus 1 is in terms of k, plus b. Okay, great. That's it. The only thing is, I assumed something about s of k. 1 second, let's just write in what we always write in. This is the new in terms of the old, but we have to fix it up. So we fixed it up, and that's exactly what's going on here. Okay, so we fixed it up. These two things, 2 times it and plus b is the fix up. Let's use our assumption here. What did we assume? So this is equal to 2 times, what's s of k? 2 to the k times a plus 2 to the k minus 1 times b. Don't forget the plus b, plus b. Okay, so this whole thing was our assumption. S of k, I just rewrote s of k right over there. Okay, I'm sorry, this needs parentheses. This needs parentheses. Great. Now, I keep an eye on my cheat sheet. And I see what I want to get. So let's multiply this out. 2 times 2 to the k is 2 to the k plus 1. I like that. Times a times, I'm sorry, plus 2 times, let's do this slowly. 2, good Lord, 2 times 2 to the k is 2 to the k plus 1 minus 2, let's do it slowly, 2 to the k plus 1 minus 2 times b, okay, plus b. Okay, let's rewrite this. Let's get rid of that. So this becomes 2 to the k plus 1 times a plus 2 to the k plus 1, I like that, minus 2b plus 1b is minus 1b. I'm sorry, minus 1. Minus 2b plus 1b is minus 1 times b. And that, sorry, I got to do what I do by mathematical induction, is equal to that. So it matched up with our cheat sheet. We're very happy. It worked. Okay. A few more small examples of these recursive definitions. But this is a recursive definition. This is a theorem. Gives it a non-recursive definition. And we used mathematical induction to prove this theorem. So that's nice. Okay, so this is a funny thing because I'm not going to define a sequence. I'm not going to define a sequence of numbers here. I'm going to define a sequence of functions. I'm going to tell you lots of different functions here. So let's do it. So this is an example. Okay. Let f go from S to S. S is a set, and f is a function from it to itself. Okay, and we're going to define the following. f1 is the base case that's equal to f. No problem. That's the original function. No problem. Okay, and now f of n plus 1, I'm going to put that in parentheses, is equal to f of n compose f. Okay, let me draw you a nice picture of this. Okay, you have a set S. You have a function from S to S, f. Great. Now, this takes in a guy here and puts out a guy here. No problem. Great. But now I want to do the following. Let's say I want to do, well, let's just do f3 for a second. f3 is equal to f2 composed f. What's f2 equal to? So this is equal to f1 composed f composed f. Great. What's f1 equal to? F. So this is f composed f composed f. Okay. So f of n plus 1 is simply another way of saying f composed f composed f composed dot 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 composed f n plus 1 times. Okay. Keep on doing it. So take this function f, but I can get another function called, do it like this and take it out like that. So this is f2. And then you can go dot 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 f of n. You have many different functions, and then basically just composing with themselves over and over and over. Okay, so that's nice. Next. Here's another interesting definition. SEQ, sequence 0 is equal to 0. Sequence of n plus 1 is equal to 1 over 1 plus sequence of n. What the hell is that? Okay, anyways, it's the n plus 1 thing is determined in terms of the nth thing. That's fine. Well, let's figure out what sequence of 3 is. Okay. This is equal to 1 over 1 plus sequence of 2 is. What's sequence of 2? So this is equal to 1 over 1 plus 1 over sequence of 1. Fine. What's 1 over 1? What's sequence of 1? So this is equal to 1 over 1 plus 1 over 1 plus sequence of 0. Okay, what's sequence of 0? That's 0. No, maybe I should have gone further. Nope, mistake. Okay, what's sequence of 1? It's 1 over 1 plus sequence of 0. Okay, great. Now we've got to calculate. So this becomes, okay, this is 0. So this becomes 1. Okay, so now let's do this. This becomes 1 over 1 plus 1 over 1. This whole thing is 1. So this is 1. 1 plus 0, this is 0. So that's 1. 1 plus 1. So this is 2. Okay, let's figure this out. So 1 plus a half, so this is 1 over 1 plus a half is 3 over 2, and 1 over 3 over 2 is 2 over 3. Okay, you should try a few other values of sequence, you'll see this. These are called I don't know, continuing fractions. And believe it or not, about 2,000 years ago, the ancient Egyptians were very much into these things. I don't know enough about it, but I'm sure Wikipedia does. Okay, now I want to do, this is homework 4B. Well, this is exercise 4B. They have two different sequences. So we're going to do 4B and 4C. Okay, here's one. 2 to the 2, 2 to the 2 to the 2, 2 to the 2 to the 2 to the 2, etc. That's 1. And here's another one. 2 to the 2, same thing so far, but here we do the following. 2 to the 2 squared, and this one is 2 to the 2 to the 2 to the 2. Okay, now what they want you to do is, and dot 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 dot. What they want you to do is write these as inductive definitions. Give inductive definitions. Did we call them inductive definitions? Recurrence definitions for these things. And it's not hard. It goes as follows. This one is SEQ 0, it's the 0th one, is equal to 2. Okay? And this one is, what do you do next? SEQ to the n plus 1 is equal to 2 times SEQ to the n. Notice what's going on here. Okay? Here's 2. 2 is up there. 2 to the 2, 2 to the 2 is up there. 2 to the 2 to the 2, it's up there, etc., etc. So just take the previous one and 2 to the sequence of that. As opposed to that, what's this? We'll call this SEQ prime of 0 is equal to 2, and SEQ prime of n plus 1. Stop the machine and try to do it on your own. Okay, stop the machine and try to do it on your own. And you can see, okay, this is equal to SEQ prime of n squared. By the way, so that's different. Here you're doing exponent, here you can do squaring. By the way, which one grows faster? Let's go through this. Let's put down number values here. Now the first two are pretty simple. This is 2, this is 2, this is 4. What's this? What's this? Let's go through this. This is 2 to the 2 is 4, 2 to the 4 is 16. What's this? 2 to the 2 is 4. 4 times 4, 4 squared is 16. So far the same. Interesting. So here they're the same, here they're the same. Let's do this. Here it's 2 to the 2 to the 2 is 16, 16 squared. So this is 16 squared. What's this? This is 2 to the 16. Okay. 16 squared is something like 256. I think it's 256. You gotta check it out yourself. I could be wrong. 2 to the 16 is something like 64,000, etc., etc. This grows, exponentiation grows much faster than that. Okay, so it's an interesting, different things. What we see from here, and here it doesn't work because it looks true, but what we see from here is as follows. Exponentiation is not associative. Well, let's not write that up. Okay, but anyways, so there are two different sequences. Great. One last example and I'll let you go. Okay, the last example is right over here. You know what? I'm just going to write the answer. This is number 8 in the homework. I think it's a homework question. And so we'll just leave it for you there. Hold on. Section 4.2. Okay. I'm not going to read the question. I'm just going to go through the answer and give you the answer. Okay? And while you're doing it, you can read it on your own. So this is number 8 in the homework. Sorry, it's not in the homework, it's in the exercises. Okay? But the book has about 10 definitions themselves. You have to read the book, but besides that, you have to do this. So S of 0 is equal to 1. It's the empty word. S of 1 is equal to 2. It's A and B. Again, you have to look up what this is talking about. It's talking about something in words. S of 2 is equal to 3y, because you have AA, AB, BA, BB, okay, but cancel out the AB. There's 3 of them there. S of 3, again, you have to read what this is talking about beforehand, is equal to 4y. I'm going to look at 3-letter words, AAA, AAB, ABA, ABB, BAA, BAB, BBA, and BBB. Let's make sure we have 8. 1, 2, 3, 4, 5, 6, 7, 8. But we're canceling out all the ones with an AB in it. So this has an AB in it. This has an AB in it. And this has an AB in it. Okay, and what's left? 1. Messed up. Sorry, this has an AB in it. 1, 2, 3, 4. Okay, and guess what? S4. I'm not going to write the whole thing. Okay, I'm just going to give you I'm not going to write the whole thing. I'm just going to write the answer. We want all words that do not have an AB in it. So watch what we have. A, 4-letter word without an AB in it. Okay, B, B, whoops, that's 5. Okay, B, A, and finally B. Takes care of that. Okay. Conclusion: S of n plus 1 equals S of n plus 1. This is the number of things. You add 1 to it. Okay. There's always one more. And the point is, the one more is the place where you change the A's into B's. Okay? So here you have A, BA, BB. AAA, BAA, you're changing it. Okay, so that's it. That's the end of the recursive definitions. Have a wonderful day. It's not a hard chapter. You got to do it. We're going to have lots of homework problems from it. Take care.